elimination. So as a summary, we said that E2 elimination is carried with tertiary alkyl halides. This reacts faster than a secondary alkyl halide. Primary alkyl halides will work, but they require to have a bulky base. Let's have an example in here. So if we have this primary alkyl halide in there, and we are reacting this with potassium tertiary butoxide in presence of a polar protic or aprotic solvent. It honestly doesn't matter here. This is polar aprotic solvent. So the first thing that you do is you locate your alpha carbon and then your beta carbon in there. We mentioned something about stereochemistry, that the beta hydrogen needs to be in opposite plane of the halogen, because the halogen has all lone pairs, and the bulky group is not going to attack from the same side of the halogen. Here I can easily rotate around the carbon, single bond carbon, and the beta carbons, so that to rotate the hydrogen and make it an opposite plane with respect to the halogen. So we need the hydrogen in opposite plane with respect to the halogen. So you go ahead and you rotate. Now, since it's a single bond, it is not a must to rotate, but it's always preferred to show whenever the base attacks to take the beta hydrogen, that the base needs to take the beta hydrogen that is in opposite in plane from that of the leaving group. So you have your base in this case. So the base is going to come from the lone pairs, not from the negative charge. The base is going to come, it's going to take the hydrogen, it's going to form a double bond, and the halogen is going to leave. This is a mechanism for the E2 reaction where it happens in one step. So in this case, my product is going to be an alkene. So I formed an alkene in this case. Whether I draw the alkene like this or I draw the alkene like that, these two are going to be the same. Please pay attention to the number of carbons. You started with 4 carbons and you should end up with 4 carbons. Let's have another example. So if we have still a primary alkyl halide, let's do the OTS. This is an alkyl leaving a group in there. OTS is a better leaving group than the halogen, and we're reacting it with potassium tertiary butoxide. This is another way how I can write the potassium tertiary butoxide or the tertiary butoxide group if I want to use the skeletal form in there. And here I am using DMSO. Then again, you're going to locate your alpha carbon, and then you're going to locate your beta hydrogen. In this case, we're going to make the beta hydrogen in opposite plane of that of the OTS. And then the E2 mechanism is whenever you start with the base is going to come, take the beta hydrogen, form a double bond, and the OTS is going to leave. So your product is going to be an alkene, and you're going to always get in these types of reactions, because it is a primary alkyl leaving group, you are going to get just one alkene product. So this is going to be the E2 product in this case. Bulky bases always happen with elimination. Whether you have heat or you don't have heat, the reaction is always going to be carried, and your product is always going to be an E2 elimination. Bulky bases can never act as a nucleophile, so there is no way that this is going to come and attack the alpha carbon and do the SN2 reaction. So with bulky bases, you always get the E2 product only. You never get the SN2. Let's say now we want to start with a secondary alkyl halide. Okay, my leaving group here is iodine. And iodine is the best leaving group along all the halogens, because iodine is an I- that comes from a strong acid. So this is going to be the weakest base, which is the best leaving group compared to the bromine and the chlorine. So if I'm reacting this, let's look at our table in here. If I'm reacting this with a methoxide group, okay, so I'm having a methoxide group. Methoxide is a strong nucleophile and a strong base. So methoxide is going to proceed by both by SN2 and E2 mechanism. E2 is going to be a major product if there is heat involved. If there is no heat, then you're going to write both the SN2 and the E2. So we're going to write both if we don't have heat. So if no heat is present, then you're going to get both SN2 and E2. So let's assume that there is no heat and write both products in there, the substitution and the elimination. Notice that the twos happen together and both are one step. So we're going to start with the SN2 reaction. Starting with the SN2 reaction, this is going to act as a nucleophile if I am considering the SN2. And the nucleophiles, they attack directly the alpha carbon from the opposite side of the leaving group because this is a chiral center and the halogen is going to leave. So you're going to end up getting your SN2 product in this case, and the SN2 product is going to proceed by inversion in configuration. So your OCH3 now is going to be behind. See, I added the OCH3 here, and the OCH3 attacked the alpha carbon, iodine left, so the OCH3 is going to be behind. There's going to be behind. The configuration for this chiral center, since the hydrogen is behind, this is an S counterclockwise, so this guy is going to be an R, and this is going to be the SN2 product, which is going to proceed by inversion in configuration. Now, with respect to the elimination, with respect to the E2. Now, E2 happens whenever the OCH3 acts as a base now. So if the OCH3 acts as a base, then in this case, E2 is going to happen. And for E2 to happen, as we mentioned before, it's a one-step reaction. So let's go ahead and write the reactants again. Iodine is in front, okay? And I am reacting this with now my base. So we said that all nucleophiles are bases, but not all bases are nucleophiles because bulky bases are polar nucleophiles. So this one over here is a strong base that is going to proceed by an E2 elimination based on this table over here. So you're going to have your E2 elimination there. So with the E2 elimination, the condition here is that the base is going to come and pick up the beta hydrogens, all the beta hydrogens. Here I do have two types of beta hydrogens. I have a beta hydrogen here because beta hydrogens are adjacent to the alpha. So I have a beta hydrogen on this side and I have a beta hydrogen on the other side as well. So let's go ahead and consider the beta hydrogen. I need the beta hydrogen that is anti-periplanar to the iodine. So these two, they need to be anti-periplanar because we agreed that iodine has lone pairs around it, so the OCH3 cannot attack from the same side of the iodine because they're going to repel each other. So it needs to attack from the opposite side to pull out the beta hydrogen. So here are two types of beta hydrogens, beta 1 and beta 2. Always consider all types of beta hydrogens. You're going to get more than one alkene in your product, and then at the end, you're going to apply the Zaitsev rule and choose the most substituted alkene. So your base is going to come over here and take the beta hydrogen. And notice that I chose the beta hydrogen that is behind, which is opposite to the iodine in there. And this is going to form a double bond, and the iodine is going to leave. So the first elimination E2 product is going to form the double bond here between those two carbons in there. This is going to be the first E2 product. Plus, there's another beta hydrogen. Actually, there is a hydrogen over here. So I'm going to pick the hydrogen that is here. We know that we have another hydrogen in plane and another hydrogen which is in front. So I'm going to pick the hydrogen which is at the back over here so that the base can come again, take that alpha hydrogen. Here you go. I'm going to use the same lone pairs in there. Doesn't matter what lone pairs you use. So that base is going to come, take the beta hydrogen, form a double bond, and iodine is going to leave. So the different beta hydrogens are going to produce different alkenes. So now my double bond is going to be on this side, and you're going to end up getting your second alkene. Once you get all the alkenes from the beta hydrogen, now what you need to do is highlight your double bond and see what degree of substitution you have around the alkene. The more, the better. So the more carbons around the alkene, the better. This alkene has 1, 2, and 3 carbons around it. So this is a tri-substituted alkene. This alkene has only 1 carbon around it. So this is a mono-substituted alkene. So what we're going to do over here is simply circle this one. And we're going to say that this guy over here, it's going to be our Zaitsev product in there. And that Zaitsev product is going to be our major product. And the reason why this is a Zaitsev product, because it is the most substituted alkene. So for this reaction, we ended up getting 3 products. We ended up getting the substitution product, and we ended up getting the substitution product, plus we ended up getting the elimination product in there. And the elimination product, you pick the major one and you write it down. You don't have to write both of them. So the major one was this one. So this one was the E2 product. So you got over here 2 products. You got the SN2 product and you got the E2 product, which is the major one. Let's say if you have heat in here, then in this case, just state the E2 as the major product. Don't even mention the substitution product. Let's have another example. And we are reacting this with NaNH2 in presence of heat. So by looking at our table, our nucleophile base table, NaNH2 is an NH2 negative, and this one is again a strong base in there. So that strong base is going to favor SN2 and E2. It's a strong base and it's a strong nucleophile. However, there is heat. So there's heat just E2, so I need only to show the E2 elimination. So now your NH2 is going to act as a base. So this guy is going to act as a base because the mechanism is going to go by E2 only. And we know the bases are going to come and take the beta hydrogen. So you locate your alpha hydrogen. This is going to be your alpha hydrogen, and you have 2 beta hydrogens in this case. Always look for all the adjacent carbons around the alpha hydrogen. So this is going to be beta 1, and this here is going to be beta 2. With E2, the hydrogen, the beta hydrogen, and the alpha leaving group, they have to be anti-periplanar with respect to each other. So the beta hydrogen and the alpha leaving a group, whether the leaving group is a halogen or an OTS or an OMS, they have to be anti-periplanar with respect to each other, meaning that they are in different planes. So now by looking at beta 1 has the ethyl group to be in front, but the hydrogen is behind. So there is no way that elimination can happen on beta 1. The base cannot come on beta 1 and take the hydrogen because the hydrogen is in the same plane of the bromine. On the other hand, in beta 2, I do have 2 options here. I do have the hydrogen which is in front, and I do have the hydrogen which is behind. So I can easily pick the hydrogen which is in front and allow the base to come and take that beta hydrogen, form a double bond, and the halogen is going to leave. Notice that the double bond that I am forming is between the 2 carbons, the alpha and the beta. This is how you do it. You form the double bond between the alpha and the beta in this case. So the base is going to come take the beta hydrogen, form a double bond, and the halogen is going to leave. And I use the hydrogen that is in different plane of the bromine. So my only elimination product for this reaction is going to be the double bond on this side over here, and then I do have my ethyl group. Always the product of elimination is an alkene, and this alkene is going to be my major alkene. I will not have a double bond between the alpha and beta 1 carbons. Let's say if I have another example, I have an alkene, and then I have my iodine in here, which is in front, and then I have a CH3, and I am reacting this with a CH3, carbon, a triple bond carbon. This is sodium acetylide, which is, if you look at the table, it is this nucleophile over here. So this is a strong nucleophile, and it is a strong base as well. So if there is no heat involved, then this guy is gonna form two products, the substitution and the elimination. Let's do both of them. So let's start with this guy acting as a nucleophile. So for the SN2 reaction, so for the SN2 in there, here I'm going to end up getting the SN2 plus the E2 as well. So for the SN2, this is going to attack from the opposite side of the leaving group as before. Since this one is a chiral center, the reaction is going to proceed by inversion. And you're going to end up getting a double bond in there. And the leaving group is going to be the iodine. And you're going to replace that iodine with the triple bond. So you're going to end up replacing it with a triple bond. And on the triple bond, you do have a CH3 in there. This is a carbon and this is a carbon. Don't miss the carbons. These are two carbons in here. Okay. And then you have the CH3. And you made a bond between this carbon, and this is the sigma bond that you made. So that is going to be my SN2 product. And it's going to be behind, so please show it behind because the reaction proceeds by inversion in configuration. And there, plus. Now for the E2, this is going to act now as a base. And bases are going to take the beta hydrogen. So I have now to locate my beta hydrogen in this case. Let's use this color. So this is going to be my alpha carbon, and I have here a beta carbon. And this guy is also a beta carbon as well, although this one has no alpha hydrogens here. So there is no, beta hydrogens. So there's no beta hydrogen, so there will be no elimination on this carbon. There will be an elimination on this one over here. So I'm just going to go ahead and pick the hydrogen, which is opposite and plane to the iodine. So the base now is going to come. It's going to take that hydrogen. It's going to form a double bond, and the iodine is going to leave. So my double bond is going to be between the alpha and the beta carbons. And you're going to end up getting my elimination product. And the elimination product is going to look like this now. And the double bond is going to be over here. This is going to be the only elimination product because I only have one type of beta hydrogen. Let's say, for example, if we had a tertiary alkyl halide. So if we had a chlorine over here and another CH3. So we're starting with a tertiary alkyl halide. And we are using a strong nucleophile and a strong base, something like an AOH. So now I know that since I'm starting with a tertiary alkyl halide, there is no way that I'm going to end up getting my SN2 product. So my product is going to be E2 product only. This reaction is going to proceed with heat. The moment I say elimination product as a major, this means that I need to have heat in there. And the mechanism is going to proceed by choosing the beta hydrogen. Let me go ahead and write another carbon in here so that I'm creating 3 different beta hydrogens. So this is going to be my alpha hydrogen. I have 3 different beta hydrogens in there. So this is going to be beta 1, this is going to be beta 2, and this is going to be beta 3. We know that we have a free rotation around the carbon, single bond carbon. So make the hydrogen anti-periplanar with respect to the halogen. So this is going to be the hydrogen here, this is going to be the hydrogen here, and this is going to be the hydrogen there. This is beta 3. Make it beta 3 over there. And then let's go ahead and start with each one. So the base is going to come, take the beta 1 hydrogen, form a double bond, and always the double bond is going to form between the alpha and the beta. And then the halogen is going to leave. This is going to be my first alkene that I will be forming. So the first E2 product is going to have a double bond here, and then I'm going to end up getting the rest of the alkenes in there. Plus, if the base come and attacks the beta 2 hydrogen, so the base is going to come attacking the beta 2 hydrogen, forming a double bond, and the halogen is going to leave. So now I'm going to end up getting a double bond between beta 2 and alpha. So my product is going to be another alkene, another type of alkene, where the double bond is here. You can easily see that this alkene is more substituted than this one. So this is going to be the major compared to both of these. This is more substituted because if you take a look at the alkene here, so this is my alkene, this alkene is connected to 3 carbons. So this is a tri-substituted alkene versus this alkene over here that is connected to 2 carbons, which is a di-substituted alkene. So this one is going to be major and this one is going to be minor. I'm not done yet. Let's go ahead and finish the third alkene where the base comes and takes the beta 3 hydrogen. So if this is the case in there, then let's use this kind of color. So the base comes over here and takes this beta hydrogen, form a double bond, and the chlorine is going to leave. So now I am going to end up getting a double bond between the alpha and beta 3. And my product is going to look like that. This is going to be now my alkene product in this case. So here you go. I do have my alkene product. This one again is going to be a tri-substituted alkene. This is a tri-substituted alkene and this is a tri-substituted alkene as well. So in this case, you can consider both of these since they are the same degree of substitution. We're going to consider both of them as the Zaitsev products, which are the major one. These are the most substituted alkene, and this guy over here is going to be the minor product. Another example is whenever we are using, let's say, for example, a secondary alkyl halide. Okay, and I am reacting this with a bulky base, like potassium tertiary butoxide or lithium diisopropylamide. Let's do the LDA. So I'm just going to write it as LDA. This is lithium diisopropylamide. So this is its structure in there. You have 2 isopropyl groups next to the nitrogen in here, and lithium balances the charge. So LDA now is going to be our bulky base, and that bulky base is going to favor the E2 elimination. If you're not working with a primary alkyl halide, so if you're working with a secondary or a tertiary alkyl halide, and you're using a bulky base, bulky bases are very bulky. If you have 2 different types of hydrogens, of beta hydrogens, here I do have 2 different types of beta hydrogens. I have a beta hydrogen that is at the back here, and I have another beta hydrogen in there. Since this guy is very bulky base, bulky bases, they need room when they attack. This is always the case. It's not like small bases. Small bases are going to favor to come and take this hydrogen here, form a double bond to make the Zaitsev product, which is the most substituted alkene. But bulky bases, on the other hand, they are so bulky that they cannot come and attack this more substituted beta carbon to take that beta hydrogen. They're going to favor to attack the less substituted beta carbon. So bulky bases, they always attack the less substituted beta carbon, in this case, to form the less substituted alkene. So the less substituted alkene in this case is going to be our Huffman product. So in summary, whenever you are working with a bulky bases are going to come and take the less substituted beta hydrogen in order to form the less substituted alkene, which is the Hofmann product. So my reaction or my mechanism is going to be from the base towards that less substituted hydrogen in there, forming a double bond, and the halogen is going to leave. So my product, major product, will be a double bond that is less substituted, and this is called the Hofmann product. You will not form the Zaitsev product. This is the Zaitsev product here, and you will not form the Zaitsev product. Now, if you are working with the cyclohexane in a chair conformation, then pay attention to the stereochemistry of the reaction, where the base needs to attack the hydrogen that is anti-periplanar with respect to the halogen. And the only way in a chair conformation for the hydrogen to be anti-periplanar, it means that they need both to be trans and diaxial with respect to each other. So the chlorine needs to be in the axial position, not the equatorial position. If the chlorine is in the equatorial position, the reaction will not happen. So the chlorine will be in the axial and the hydrogen will be in the axial. And the base is going to come, take the hydrogen, which is an opposite plane. It's an anti-periplanar with respect to the chlorine. So it's going to take the hydrogen, form a double bond, and the halogen is going to leave. This is another example where you can change the cyclohexane into a chair conformation. It is not a must to change into a chair conformation. You can easily figure it out from here that that the hydrogen on this beta carbon, this is beta 1, and you have beta 2 over here. So with beta 2, you can have hydrogen which is in front and behind. So you can pick simply the hydrogen that is opposite in plane to the chlorine and do the elimination. But on beta 1, your hydrogen is in front, which is on the same side of the halogen. So we know that elimination cannot happen on beta 1 and it will happen on beta 2. This is what I'm saying over here. Whenever you change it into a chair conformation, you can easily see that on beta 1, the hydrogen is equatorial. It's in the same plane as the chlorine in this case. It's on the same side of the chlorine. So this is why elimination cannot happen. For elimination to happen, you need the hydrogen and the halogen to be anti-periplanar, and with the chair conformation, you need them to be trans-diaxial with respect to each other. So for this one, if I pick the hydrogen which is down, then this is going to be on the axial position. These two are axial, so yes, elimination can happen in there, and you can get the double bond on this side.